The day a grain of sand hit Earth at near light speed. Imagine a single grain of sand, seemingly insignificant, hurtling through space. Now picture it striking Earth at nearly the speed of light. This isn't science fiction. It's a thought experiment exploring the extreme consequences of relativistic physics. The impact would be a catastrophic event, dwarfing the effects of conventional weapons. The planet would experience alterations on a scale rarely seen in human history. The energy released would be almost unimaginable. The primary destructive force in this scenario is the immense kinetic energy of the sand grain. Kinetic energy increases exponentially as an object approaches the speed of light. This is where relativistic effects come into play. As the sand grain accelerates to near light speed, its mass increases significantly. This is due to Einstein's theory of special relativity. The increase in mass further amplifies the kinetic energy. The energy released upon impact would be equivalent to a substantial amount of TNT. This energy would be unleashed in a fraction of a second. The results would be devastating. The instant the sand grain makes contact, it would vaporize. The sheer force of the impact would obliterate its physical structure. This vaporization process would generate extreme heat. Temperatures at the impact site would exceed those found on the surface of the sun. The surrounding matter would be instantly superheated. This intense heat would lead to the formation of plasma. Plasma is an ionized gas, a state of matter where electrons are stripped from atoms. This superheated plasma would expand rapidly, carrying immense energy. It would be a short-lived but incredibly powerful phenomenon. The impact would generate a massive crater. The size of the crater would be far larger than the sand grain itself. This is due to the immense energy transfer. A supersonic shockwave would propagate outwards from the impact site. This shockwave would pulverize everything in its path. The surrounding materials would be instantly compressed and shattered. The crater could potentially be kilometers wide. The exact size would depend on factors like the density of the ground. The scar left behind might even be visible from space. The intense heat would cause a localized atmospheric disturbance. The air around the impact site would be superheated and ionized. This would create a temporary but powerful disruption. The powerful blast wave would potentially travel globally. It would compress and heat the air as it moves. This could cause widespread damage and disruption. Vaporized material and debris would be injected into the atmosphere. This material would consist of both the sand grain and the impacted ground. The atmospheric injection could lead to significant changes. The atmospheric changes could potentially disrupt the climate. Dust and debris could block sunlight. This could lead to a period of global cooling. The consequences would be devastating, depending on the impact location. An impact in a populated area would be catastrophic. An impact in the ocean would trigger massive tsunamis. Everything within the blast radius would be annihilated. Buildings would be flattened, and life would be extinguished. The scale of destruction would be almost incomprehensible. The impact could trigger tsunamis. These massive waves would radiate outwards from the impact site. Coastal areas would be inundated. The impact could also trigger earthquakes. The shock wave would travel through the Earth's crust. This could destabilize fault lines and cause seismic activity. Volcanic eruptions could also be triggered. The impact could disturb magma chambers. This could lead to eruptions in volcanically active regions. Debris in the atmosphere could block sunlight. This would reduce the amount of solar energy reaching the Earth's surface. This could lead to a period of global cooling, potentially a sand grain winter. The impact would result in the vaporization of both the sand grain and the target material. This would create a cloud of superheated gas and debris. The formation of plasma would be a key feature of the initial impact. Massive cratering would reshape the landscape. The crater would be a lasting reminder of the event. Global atmospheric disturbances would affect weather patterns and climate. Global geological disturbances could trigger earthquakes and volcanic eruptions. The Earth's crust would be shaken and stressed. This scenario highlights the power of even small particles at near light speeds. The energy released would be immense, demonstrating the principles of relativistic physics. It serves as a stark reminder of the potential consequences of high-velocity impacts. While highly improbable, this thought experiment provides valuable insights into the nature of energy, momentum, and the fragility of our planet.